foundations. Let me just get this out. Quantum foundational experiments using diamond MV centers. So I've actually broken up the talk into 4 parts. The first part, I will just briefly sketch what is the long-term goal of my research, so that you can see how these experiments fit into sort of a bigger picture. And then I will dive into the 3 different parts that are, I think, relevant for many of you. I will start with a very brief introduction of the general quantum control toolbox that we have in the MV Center. And then I will touch upon some experiments that we've done with nuclear spin registers. So these are really experiments on say a local number of qubits. And in the last part, I will touch upon remote entanglement experiments. And at the end, I will show you some results very fresh from the lab. So let's start with the ultimate vision. So my group works towards this grand idea of a global quantum internet, a network that will be able to exchange qubits between local quantum processors, anywhere around the globe. That's a very nice ultimate vision. Of course, it's not something that we can achieve tomorrow or in the next 5 years, but this is sort of the dot on the horizon towards we are working. Now, to make this, the road towards the dot on the horizon a bit more tangible, colleagues of myself, Stephanie Wehner and David Elkus, and me have written a perspective 2 years ago in which we actually try to break down, what steps would have to be done. And out of this, arguably, you could say that you could actually condense this whole article into this picture, because this picture gives you a sort of stepping stone of the different stages of quantum network development that we expect to have as a function of time. And so at the moment we are in the area of trusted repeater networks, which are not really quantum networks, but they are really networks of individual quantum links that are then connected classically. So these are basically the quantum key distribution links that you know of. And so the idea is that once you add functionality and the network is capable of doing more and more things, you can also use it for more and more interesting things. So the functionality is actually directly linked to certain applications, or if you want, certain scientific experiments that you could do on the network. And so, for instance, once we're able to distribute entanglement very far and at high fidelity, then we can use this idea of device-independent key distribution. I think many of you are probably familiar with that, where you really make use of the output of the devices itself to build trust in the key that you're building up. So this is the sort of very extreme picture in which none of the components you have to trust except for the output of your device. Now, if we add memory, so we can distribute entanglement and we add memory, and we can also do a little bit of computation, then we can think of applications like blind quantum computing in the cloud, where you can send data to a quantum computing server. The server will run a certain algorithm and send the data back. And in this whole process, both the data you send, the computation, and the data that's sent back can actually be shielded, can be fundamentally shielded from access by any third party, including that quantum server. Now, finally, as an example, if you get to the level of fault-tolerant few qubit networks, then you can think of applications like clock synchronization, where you actually use entanglement to achieve advantages in these type of metrology things. So these are just a few examples to show what can come, once we increase the capabilities that we have on the network. Now, there's actually many candidates for building the nodes of such a network. What I've done here is, I've listed the ones that have been able to make entanglement between separated nodes. So, they go from trapped ions that were actually the first to achieve this in the group of Chris Monroe, now already 13 years ago. Trapped single atoms that were done by Harold Weinfurt and Gerhard Remper's group. And then we have some solid state implementations and MV centers that I will talk about. But also quantum dots and actually also superconducting qubits in more recent years. And it's interesting because even though these superconducting qubits, of course, they don't have these the real macroscopic distances, at meters or kilometers that we're talking about with the other systems. But many of the techniques and methods that they are using and are also developing actually have a lot of cross-fertilization with the other platforms. So, I mean, if you step out of the actual implementation, you see there's actually these fields are actually very much connected. So this is just a list of the platforms that have demonstrated remote entanglement between two nodes, but there's actually many more nodes under development. For example, silicon carbide color centers, diamond silicon vacancy centers, and there's a range more coming up. And I think it's fair to say at this point we don't know what the eventual quantum internet, right, this global network, what it in the end will be based on. So the goal in my lab, sort of the near-term goal, is to realize entanglement-based networks of more than two nodes, and we want to do that first locally in the lab, so at a few meter distances, but then also to roll this out between cities, so to actually really use it on a deployed fiber. We have actually quite a large effort together with TNO, that's a Dutch research and technology organization, to start to implement the first link between Delft and The Hague. So that includes things like quantum frequency conversion, etc., etc. But I'm not going to talk about that in this talk. So I will actually now focus on the NV Center. So I want to dive a little bit into the quantum control toolbox to show you the things that we're able to do. And then I will go on to discuss the different experiments that have been done, and then we can get further. So let's start at the beginning. What is an NV Center? An NV Center is a defect center in diamond. As you know, diamond in its purest form only has carbon atoms. These are depicted black here. Sometimes there is a nitrogen substitutional to a carbon, and sometimes the carbon that should be next to this nitrogen is missing. It's the vacancy. So basically, if you have this, the nitrogen and the missing carbon, you have an NV center. And the NV center really acts as a trap for electrons. The NV center in the negatively charged state that we will be talking about here actually takes up 6 electrons, but we can forget about 4 of them and only think of it as a 2-electron system for most purposes. And so in the orbital ground state, these 2 electrons form a spin triplet state. There is a zero field splitting of close to 3 gigahertz between the 0 and the ±1 sublevels. And when we apply magnetic field, we can also split these upper 2 levels. So then we have 3 levels that are individually addressable. And so they are, the energy splittings are typically around a few gigahertz here. Now, the optical or the excited state level structure of the NV center is actually quite complicated. And I put here a reference to, I think, a very good introduction to that. But what you need to understand for this talk is that there are a couple of transitions that are cycling, and these are typically denoted as the EX and EY transitions, although EX and EY really, denotes the excited states. And there are other transitions. They will be called A1 and E prime. And they are more mixed. So they are not really good cycling transitions, but they are very good for spin pumping. And so you see, for instance, here that I drew an arrow here as P spin pumping. If I start to hit this transition with a laser, there's actually a decent probability that after a few cycles, I will actually end up onto this side. And so it turns out that the transitions involving the ±1 states are typically the less cycling ones, and the ones involving the M as a 0 sublevel are the cycling ones. So they can be used for readout RO. These transitions are at 637 nanometers. So this is red light purely in the optical domain, which is actually quite nice for using room temperature silicon APDs, because that's exactly where the peak of the quantum efficiency is. So virtually all the experiments I will be talking about today have been done on devices that look like this. Today we also work on different types of devices, but for this talk, let's focus on this one. So what you see here is an electron microscope picture of a piece of diamond, and a little half dome has been etched out using a focused ion beam. And it actually has been etched out right on top of an MV center that we pre-characterize. So there's an MV center right here, and we have this half dome that also has an anti-reflection coating to actually get the light out very efficiently. Now you also see here this is actually a gold strip line that we can use to apply microwaves to. And if these microwaves, I will get to that later. So let me first say how this is incorporated onto a sample holder. So actually these diamond samples are typically only a few millimeter large. So we actually bond them onto a sample holder, and these are then put into a cryostat, typically a closed cycle cryostat, where we cool them down to 4 Kelvin. And so when we apply microwave signals to these strip lines, and they are resonant with these spin transitions that I showed in the one of the previous slides, then following the magnetic resonance principle, we can actually induce rotations between these spin levels. So here's actually an example from almost 10 years ago. You can see very nice Rabi oscillations on sort of tens of nanoseconds time scale. Now, the reason that we go down to 4 Kelvin is not because of the spin control, because actually the graph you see here is made at room temperature. You can do these experiments at room temperature. But at room temperature, you do not have the optical toolbox available. So once you cool down to below about 10 Kelvin, then and you start to sweep the laser across the optical transitions, you see these very sharp lines. So these sharp lines now indicate transitions to these individual excited states, and they are spin resolved. And so using that selective excitation, we can actually now do very efficient spin initialization and readout. So the initialization is done very trivially. We just turn on a laser on one of these not so cycling transitions, coupling the plus and the -1 states to one of these excited states. And after a few cycles, we will actually pump it to the MSS0 state. Now this laser is not resonant with this transition, as you saw in the previous slide. They are really selective. So actually, if you look at the fluorescence, starting from this state, you see it quickly dies out, and in a few microseconds, you've actually initialized with very high probability into the MSS0 state. Now for the readout, we actually use the cycling transition, and we use the idea of state-dependent fluorescence. So we basically turn on this laser for some time. And the idea is that if we are in the MSS0 state, we are cycling through this transition, photons will come out, and we should be able to detect at least one of these photons. And conversely, if we don't see any photons, we actually say the state was MSS+1 or MSS-1. I should say that in most of the experiments, we actually take one of these spin sublevels ±1, and we leave the other one out, so we make sure we actually never populate that state, so we can really work with a qubit system. So what you then see is if you drive this on initial state MSS0, you get on average, in this case, about 8.5 photons. And if you are in a +1 or -1, you basically get almost no cases you actually get a photon. So the average photon number is very small. And the best fidelity we've achieved so far using this readout is 98%. Now, the MV center is not alone in the diamond. Of course, it has these carbon atoms nearby, and most of the carbon atoms are carbon-12. That carries no nuclear spin. But if you take a diamond with natural abundance, you have 1.1% of carbon-13, and carbon-13 is a spin-half system. So if you take any random MV center, you will actually have at sort of random positions, you will have a few of these spins. And these spins, of course, interact with the electronic spin of the MV center. They actually form a fluctuating path. And in a sort of semi-classical picture, you can think of all these nuclear spins exerting a magnetic field on the electron spin that is shaking in time. And this is the main contribution to decoherence inside the diamond. But actually, it turns out that if we look at the two different relevant time scales, so there's the T1 time, the energy relaxation time. This is really more than an hour. We cannot measure it in the experiments that we're currently doing. It's too long. And the dephasing time, so if we make a superposition state and we let it evolve, we can actually protect the superposition times using the techniques called dynamical decoupling. And in this case, what you do is that you apply refocusing pulses at certain regular intervals that basically decouple the spin from the fluctuating fields from above. And what you see in this plot, this is actually raw data. This is not how it was plotted in this paper, but I like this plot because you can actually see how this trend goes. So if you apply only one refocusing pulse, it's like a Hahn spin echo. You have a decay time of the coherence of a few milliseconds. But then if you start to increase the number of refocusing pulses, and they go up to about 1,000 on this side, you see that you reach beyond a second. So we can keep coherences inside this electron spin system for over a second, which is more than enough for most of the applications that we want. Okay, so these are then the basic tools that we have. We use magnetic resonance to control the electronic spin. And we use the optical transitions to do initialization and readout of the electron spin. And we can actually decouple from the environment and get access to these very long coherence times by using the decoupling sequences that actually protects the MV center from the decoherence. Now, I would like to dive in a little bit deeper because you see all these fit lines, these solid lines. And these are fits to simple exponential cubed decays as expected for a fluctuating spin path. And you see that the envelope nicely shifts to the right, showing this enhanced coherence. But actually, it turns out that if we zoom in on one of these lines and we look a bit more careful, there's actually a surprise. So what you see here is the same type of measurement for 3 different MV centers. And so the envelope that you saw before is basically the envelope of these upper parts. So you see this part slowly going down, and so this is the slowly decaying envelope. But then you see on top of this envelope, you see these sharp spikes. And some of these spikes go down to 0, meaning that in this case, the coherence of the MV center is gone. But you also see spikes that actually go below 0. And that means that there's still coherence in the MV center, but actually the superposition state has flipped sign. So something has happened, under the dynamics here that makes, does some coherent evolution to the MV center electron spin and makes it flip sign. Now, if you look at a different MV center, what you see is that these spikes occur at different times, so different interpulse delays. And they are of different depths. And I take another MV center here below, and you see again it looks quite different. So what is going on here? Well, the fact that the spike pattern is very different for each MV center already tells us it's not a property of the MV center, but it's a property of the microscopic environment. And it turns out that what we see here, these different signals, are the interactions with individual nuclear spins in the environment. They're individual coherent interactions with these nuclear spins. And why does that happen? So one way to look at that is to take the position of the nuclear spin, right? So if I take a certain nuclear spin, I have a magnetic field applied in the z direction, and that means that there's, I have some Larmor precession along that axis. And if the electron is in the state m0, then there's also no hyperfine interaction. But if then the electron goes to the state 1 or -1, the hyperfine interaction is turned on. And this hyperfine interaction, of course, is very different for each nuclear spin because it depends on the distance and the angle of the axis between them compared to the quantization axis. So every nuclear spin will have a different, extra rotation axis due to this hyperfine interaction, and we drew that here as an extra arrow here. And so if the electron is in m1, the nuclear spin will actually rotate around a different axis that is, at some angle and with a different strength. So that means that whenever we're flipping the electron, which we are doing in this dynamical decoupling sequence, we're going from one state to the other, one state to the other. For most interpulse delay times, nothing much happens. The nuclear spin just wobbles around a little bit, and that's fine. But if this interpulse delay, this up and down, actually hits a resonance namely resonance with this interaction, then we are going to coherently rotate the nuclear spin. And this is actually what we are seeing in this previous picture. Maybe I can go back to this slide. So actually what you see here, for example, this spike here we have an interpulse delay in which the nuclear spin is undergoing a full 2-pi rotation. And as you know, if you do 2-pi rotation on the spin, you get a minus sign. And that minus sign is then transferred onto the electron spin superposition state. And the electron spin goes from the plus x state to the minus x state. So it's a fully coherent gate operation, if you wish, on these nuclear spins. Now, it turns out that if you take these individual interactions and you know that you're not targeting individual nuclear spins, you can actually form a universal control over these nuclear spins. You can do any gate that you want because you basically have access to 2 different rotation axes of these spins. And so, for instance, if I want to do an interactions with this nuclear spin, but I don't want to touch the other ones, I'll make sure I rotate the electron spin at the at the pace that is good for the resonance with this guy, tailored to the interaction with this nuclear spin, and the other ones will remain decoupled. And if I then want an interaction with another nuclear spin, I change the frequency at which I flip my electron spin, and then I have an interaction with that nuclear spin. So that way I can actually get access and control the individual nuclear spins, even though there are many of them inside this spin bound. So we've used this tool of nuclear spin control in several experiments. So this experiment in 2014 was just to establish that we could actually access these different nuclear spins, as I shown before. But then if you combine this with readout of the electron spin, you can do other interesting things. For example, you can then do parity measurements, or you can do a sigma x measurement, but you can also do sigma x measurements because you have the full quantum logic on 2 nuclear spins, or sigma x on 3 nuclear spins. And we've actually used this in this paper to create quantum Zeno subspaces. So what we do is that we apply these measurements, and these measurements basically cut the available state space into 2. And now if these measurements only measure the parity and don't touch the coherences inside, then the evolution inside, of course, still happens, right? So you get evolution inside the quantum Zeno subspace, but there's no crossing over from one subspace to the other. And indeed, we showed in this paper that we can do that with up to 3 nuclear spin and actually explore these quantum Zeno subspaces. Now, people that are familiar with quantum computing know that what we're talking about, of course, is very closely related to quantum error correction. And in 2016, the group of Tim Taminio in Delft, together with my group, did an experiment where we actually took 3 of these nuclear spins, encoded a logical qubit, and did a error correction cycle without decoding the electron. Decoding these nuclear spins. We actually stay inside, do the parity measurements, do a correction, and so on. And we could show that we could actually beat the dephasing time of the best physical qubit using this quantum error correction. So that's a very nice result because it shows that it can do something. It's not yet better than anything you could do on that qubit, because there's also, we could correct for the dephasing, but we could not more efficiently correct for the other errors. Right, the 3-qubit code can only correct for one type of error, in this case, a phase flip. But it shows the combination of parity measurements and, parity, basically parity checks and the single shot readout of the electron spin. And so more recently, we've actually applied this on contextuality tests. So we did some more technical changes to the parity measurement that made it more quantum non-demolition. So they actually they were more non-destructive on the nuclear spins. And so what you see here on the left is an experiment that I like very much. It's a bit of a jungle. But what we start with here is a fully mixed state of the 3 nuclear spins. So they are in some random state. And then we start to apply these 3-qubit parity measurements. So we start with x1, y2, y3. And we get an outcome, +1 and -1. And this puts us then into one of these subspaces, right? So for example, if I get +1, I'm in the +1 subspace of this parity operator. Then I apply a second one. This is y1, x2, y3. Again, I split up into one of the subspaces and apply a third one, This is y1, y2, x3. And then, no matter where I started, I will end up in one of these 8 states. And these 8 states are all genuine multipartite entangled states. So these are GSZ states, and they differ by, for example, these two, they differ by the phase, and you can see the differences between these states. So actually, by taking a random state, fully mixed state, just applying 3 of these 3-qubit parity measurements, you end up in a fully entangled state of 3 nuclear spins. Now, you can use that then to do a GSZ test. I think most of you will be familiar with the standard GSZ test. That's also done with entangled photons by Anton Zeilinger, for instance. In those tests with photons, you actually have to prepare these states, and then you measure always one instance, right? And you have to actually sample through all these different instances, and then together afterwards you actually collect all the data and you see a violation with the classical expectation. Now, what is interesting of this system is that you can actually do this experiment in a single shot. And the way to do that is that you do actually the same that you do on the left side, but then you add a 4th measurement. And the 4th parity is actually x1, x2, x3. And no matter what happened here on this side, the x1, x2, x3, here in this case, it should always give you a +1 outcome, whereas the quantum mechanical prediction is the -1 outcome. And so by just doing that measurement immediately, afterwards, so you basically do all 4 of them in one go, you should see -1 in the quantum case and +1 in the classical case. And indeed, we see, if we apply them all, we see something that's of course not exactly -1 due to technical imperfections, but we get something that's -0.6. So the beauty of this, I think, is more in the concept that you can do it just in each shot. You get the contradiction with the classical expectation. Now, this experiment does have some assumptions, and the most stringent assumption is actually that you have to assume that when you do these parity measurements, so you do the x1, y2, y3, you are actually you have actually access to the sigma x1 observable, right, and the sigma y2 observable, etc. So you have to assume something about the underlying measurements, and that you can actually mitigate, at least partially, by adding different correlators. So you can actually extend these stacks, and for instance, Cabello has done a lot of work on this to make these solid and formal, and then you can run non-contextuality tests. And we've done one of these proposals where you basically take this, and you extend it with further measurements to do a test in 8 dimensions. And in this particular case, I'm not going to talk about that in detail. The details are in this paper, but the classical bound is C is 3, and we beat that bound by many standard deviations. Okay. Just final words on these nuclear spin registers. Just want to give you an idea of what are the most recent capabilities. And this is actually work done by my colleague Tim Taminio. So it's really work from his lab, mainly depicted in this paper, and also a paper published in Nature this year that looks more at the sensing side of these things. So actually, he took an MV center, used the intrinsic nitrogen 14, the nitrogen of the N of the MV center also as a qubit, and a 8 carbon-13 nuclear spins in the environment that he could control. And he showed that in this register, he could create entanglement, pairwise entanglement between all the qubits. So it's really actually fully connected. Any pair of qubits can make an entangled state. Some of them are just above 0.5, as you can see, and some of them are really high, close to 1. Then another thing he did is to see, how big of a GSZ state can I make with current control. And you see here, adding the number of qubits and the GSZ state fidelity, you see that up to 7 qubits, you are firmly above the bound of 0.5. So we can make a 7-qubit GSZ state inside this diamond. And another final thing that he did is to look at the coherence of these entangled states. So again, taking these ideas of dynamical decoupling, but now using them on the nuclear spins, right? Because we have full control of the nuclear spins. You can also apply refocusing pulses on these nuclear spins. He showed that you can preserve 2-qubit entanglement for over 10 seconds inside these diamonds. Yeah, so with that, I want to go to the final topic, which is the remote entanglement experiments. There we are. And so for those who are not so familiar with the way we actually make entanglement between distant qubits, the idea is very simple. You actually start by making locally entanglement between your spin state and a photon. So some degree of freedom of the photon. So there can be a polarization of the photon, frequency, it can be time bin, it can also be a photon number, as I will discuss a bit later. So you do this in a synchronized way, such that these photons, when they travel towards the beam splitter, they overlap here on the beam splitter, and then you look for detections on the output arms of the beam splitter. And in the 2-photon scheme, if you actually detect both photons, you project the spin states onto a maximally entangled state. So what is important here is that these are measurement-based schemes, right? They are intrinsically probabilistic. This scheme can, even without photon loss, only work in 50% of the time. But of course, we typically have a lot of photon loss. But the beauty is that the entanglement is heralded by these photon clicks. So many times you actually try to make entanglement, a photon will get lost, or maybe it's not even emitted at all. But those cases you can just disregard because you did not get the heralding signal. But when you get the heralding signal, in this case you get the 2 clicks, you can actually have very high confidence that there were indeed 2 photons and that the spin states afterwards are indeed entangled. So just one technical challenge that is quite relevant for any experimentalists that may be in this talk, because we are coming in with a laser beam trying to do this excitation of the MV center to make it emit a photon. This is typically done using sort of 1 or 2 nanosecond optical pi pulse. And this pulse contains, thousands, tens of thousands of photons. We shoot them towards this diamond. Many of these photons also come back. And then out of these many photons, we have to actually single out this one photon that the MV center emits. And of course, this MV center emits at exactly the same wavelength. So there's no way that you can do simple wavelength filtering. And so what we do in these experiments is that we apply 2 types of filterings. We have a cross-polarization filtering. So we make sure that the excitation light is actually perpendicular or almost perpendicular to the dipole that we are exciting. And then we put a polarization filter in the detection path that blocks out all the excitation light, but lets through most of the emission light. And the second part that you can see actually in this graph is that we do detection time filtering. So what you see here, this is as a function of time. You see the blue pulse is if we only apply a laser pulse, you actually see light that is reflected from the diamond. And then in red, you see what happens if we are also on an MV center, so resonant with an MV center. And then the most important part is this part, because you see here the exponential tail. This is a log scale, the exponential tail showing the single photon emission of the MV center. At some point, this actually drowns in the background noise because you get dark counts from the silicon APD. And on this side, of course, if you get a photon detection, there's a very high probability that it was actually not an MV center photon, but it was a scattered laser photon. So what we do is that we apply a time filter and we say only photons detected in this time window are valid. Right? If we don't detect them here, they do not count, and we're not sure that we actually made them time. So by doing this time filtering, you can play with this quite a bit. You can get very high. You can be very confident that when you get a click, it was actually an MV center photon. And so this experiment we did about 8 years ago already in the lab, published in 2013, between 2 setups separated by a few meters. You see all the optics on the table. In more recent experiments, we've removed virtually all the optics. And this is now all in fiber these days, so the experiments look much cleaner, perhaps less impressive. So 2013, we did the first experiment, as was mentioned in the introduction. We also used this to do a teleportation experiment in 2014, actually between one of these chips and the other side. And then in 2015, we managed to use this for a loophole-free bell test. So in this case, we actually took one of the setups very far away, 1.3 kilometers out, and we had the heralding station sort of in the middle. And this experiment was actually tricky because it had to combine all these things. So everything had to be high fidelity: spin reset, remote entanglement, the single shot readout, and we were using different labs. So many things that you want to do inside a single lab to synchronize things cannot be done at a distance. So there are many things that had to be invented and operated there. And some of these things we actually still use today, and they come in handy if you're not allowed to enter the lab because of COVID-19. So if you just look at the numbers, the distance here a bit more than a kilometers, we got now entanglement fidelity is about 0.9, but the entangling rate was very low. This is millihertz, and in this experiment, no memories were used. I will not talk about that. Actually, to get the entanglement rate up from this very low rate, we actually looked at the different schemes that were available to us. So what I explained so far were two photon schemes, and in two photon schemes basically rely on the fact that the case where you detect two photons, and both were reflected at the beam splitter, cannot be distinguished from the case where two photons were transmitted. And that means that, right, the case where the detection of the left detector corresponds to a photon from the left side is indistinguishable from a photon coming from the right side. So this scheme is nice because it only requires overlap of photon wave packets, which are several meters long. So it's very easy experimentally, but the success probability scales quadratically with photon detection because you need to detect both of the photons. Otherwise, you cannot herald entanglement. Now, there are other schemes proposed that make use of something else. Namely, you herald on detection of a single photon, where the single photon can now have come from the left or from the right, and you make sure that the probability that there were two photons to start with is actually very low. So this does require more overlapping precision. Actually, it requires phase stabilization, as I will show you in the next slides. But the success probability scales linearly with the photon detection probability. And that, in the high loss regime, this is actually very advantageous. So a couple of years ago, we started to investigate this. And so what we now had to do is that if you look at this, the setups of the two diamonds, excitation pulse, single photon emission to the beam splitter, we actually had to stabilize this interferometer. And so what we did is to alternate entanglement generation with phase stabilization. And we did that in this case every 180 milliseconds. It was a kind of a crude way. There was some feedback mechanism with a fiber stretcher, but it worked well for this first experiment. And we could show indeed, what you see here is state fidelities of entangled states that we could make, and success rate as a function of the bright state population. So actually the probability that the MV center would emit a photon. And you see there's some optimal point here at which we reach 81% fidelity already in this first experiment. But the rates are now in tens of hertz. So many orders of magnitude faster than what we had before. And this brings us into a new regime, because if we now compare the entangled state generation, like how fast can I make entanglement, to the decoherence rate at the nodes, and you can define the ratio of these, what we call quantum link efficiency. And if you can do this, quantum link efficiency larger than 1, it actually means that you generate entanglement faster than that you lose it due to decoherence. And in the experiments we did 2 years ago, we could actually show that this fast entanglement generation at sort of a 10 hertz level, combined with protection of the entanglement using dynamical decoupling, and they only decay at 5 hertz, we actually got up to quantum link efficiencies up to 8. So we actually were now able to cross that bound. And it's quite interesting if you look at the evolution of sort of the time it takes to make an entangled link and the quantum memory time. You see that they actually indeed cross here in 2018, and they, together they actually bridge about 6 orders of magnitude. So there's been a rapid increase in the functionality of these nodes. So then finally, I want to discuss very briefly experiment we did very recently. So this is fresh data, not published yet, no paper has been written yet even. But so what we do now is that we have two of these NV centers. These are the same setups that you saw in the previous experiment. We add a memory on one of them, so on the Bob side, and then we have another node that is actually in a different room, Alice, that also holds one NV center. And so we have sort of this setup. Don't worry too much about all these different signs here. Just, if you want to understand a little bit what the capabilities currently are, so we can do this initialization quite fast, much better than 99%. In this case, single shot readout of all the nodes was above 95%. Single qubit fidelities are of 99%. 2 qubit gate fidelities, so inside this node, are about 98%. And in this experiment, so I'm not going to dive into that now, but we actually solved many interesting challenges to realize scalability into this 3-node network. But they are beyond the scope of this talk. But in this network, we are now able to make entangled states both on the Alice-Bob link and on the Bob-Charlie, without changing anything in the setup. So this is all software controlled. We can just choose to make entanglement on one of these links. And so one of the experiments that we did now was to use the middle node as a sort of a quantum repeater node. So to distribute entanglement between A and C, make an EPR pair between A and C by using the middle node as an intermediary. And so it has the following steps. So we make first entanglement between A and B. Then we swap this half of the entangled state at Bob into a quantum memory. Then we make an entangled state at B and C. And then we perform a Bell state measurement at B, which basically teleports this entanglement out to the outer node, making the EPR pair that we want. And so in this case, I just flash the correlators that we measured on the outer nodes after this protocol. And we see that indeed, we now achieve a state fidelity above 50%. So this protocol actually nicely works to do, distribute an EPR pair between two non-neighboring nodes. We also did another experiment where we made a GHZ state, and we showed that we have genuine multipartite entanglement across the 3 nodes. And that will be also in the work that we're currently writing up. So that's very new, very exciting, because now we are in a position to actually start to use multiple nodes in different types of experiments. Of course, we can still work on the fidelities, etc. But the architecture is there, and the control is also there. And I think this is, that bodes well for the next years. So with that, I want to end this talk. I want to thank you for your attention. I want to thank the people in my group, current and former members, my collaborators, funding agencies. You can see here a clearly pre-corona picture when we were still allowed to make fun in the lab. Altogether, hopefully we will return to those days very soon. For now, thank you very much for your attention. I'm happy to answer any questions you have. Thanks.
So thank you very much, Ronald. It's a fantastic talk. We really enjoyed it. And to the audience, if do you have any question for Ronald, please ask.
So very interesting talk. So maybe I will ask one question, and then maybe others can also should ask questions. So this capability that you showed in the middle, that you have these nuclear spins also under control, right? So are you progressing towards how to use them for like building repeaters and stuff? So once you have connected these nodes, like in this entanglement establishment that you spoke about, so we also did this heavy things. So there, if you have ancillary things, you can kind of repeat and do better.
So what is nice about this system is that each of these NV centers, these devices we work, they have several of these nuclear spins that we can control. And the control techniques themselves are good enough, so the fidelities are high up in the 90s. The challenge that we're currently working on is that if you store a state on these nuclear spins and then you start to use the electron spin for entanglement generation, electron spin is often in a state that you don't know, because most of the times the entanglement generation fails, and then you don't know what the electron state. So we're working on different types of protocols to actually make sure the nuclear spins are not sensitive to that anymore, and they look like they actually been very successful. So we have some other unpublished data that looks like this, which actually this used to be the bottleneck in previous experiments, but it looks like this is not a bottleneck anymore. So I'm actually very hopeful that we can increase the size of these local registers to multiple nuclear spins, and then indeed start to use them, to more complicated experiments. Yeah.
Okay. No, that's very interesting. Yeah. And one quick thing, just information: how many pulses for the seconds of coherence times? How many dynamical decoupling pulses at 4K does one need usually?
Yeah. So if you have, if you look on the electron spin, you have a natural abundance of carbon-13. Then at, I mean, if you want a second, this is above 1,000.
1,000.
Yeah. So it's between 1,000 and 10,000 or so. Yeah.
Okay.
Yeah, it's a lot of pulses. But the interesting thing is that once the fidelities of these pulses is high, and of course you can run these in pulse sequences that have intrinsic error compensation. Right, so these are all known from NMR. So you concatenate them in sort of it's called like XY8. So you rotate along different axes, etc. So actually the fidelity of these operations is extremely high. So even if you apply 1,000 pulses, there's hardly any decay due to the pulses. Yeah.
Okay.
Yeah.
Anupam,
Oh, sorry.
sorry, I'd raised hand, but never mind. Yeah.
Mercy. Yeah.
Yeah. So yeah, Ronald, a very nice talk. So just a quick question related to exactly what you said just now. So how does this compare with? I mean, I'm thinking we can also have these little NMR systems which are kind of linked together the same way. So we are talking NV centers now, but then suppose we, you are again dealing with nuclear, the nuclear spin. And so how does this compare in contrast with our conventional NMR-based approach?
Yeah, I think there are actually many similarities with the NMR-based approach, because in principle what we're doing is it's kind of NMR, but then on a single centers, right?
Yeah.
So that means that at least if you think about the ensemble NMR approach, you have the scalability issue, right? You cannot, you can add a few nuclear spins and more nuclear spins. At some point it just stops. And that scalability issue is of course also there for the NV centers, but we have the optical links to actually create more scalability. So if people think about building larger processors, for instance, with NV centers, it's really in this the idea of modular architecture, where you will have small modules, maybe 10 qubits that are then optically linked together, to form a bigger processor or a network, if you wish. And if you think about control techniques, they are very, very similar. And actually, the way this field has developed is that, I mean, we did this first experiment now 10 years ago, in which we showed that we could protect any qubit state on the electron spin of the NV center. But this has rapidly moved on to nuclear spins, and it has a big impact on the sensing community. So, I mean, I did not talk about that at all, but a lot of people are using NV centers for sensing. And they have taken, basically the first thing that this community has done is take the NMR books and copy them onto the single centers. But then, because you're looking at individual centers and you have this single shot readout, there are actually more things you can do. So I think it's fair to say now that the NV center community has moved beyond what was already established in NMR. And the kind of tricks that people are now doing to enhance the sensitivity is actually quite amazing. But they are, one could say they are really advanced NMR techniques. Yeah.
So then a quick follow-up before I mute. And so then what is so now, of course, there's a difficult question, because, I mean, it was a great talk. So, but then, so what is the bottleneck of NV centers? So how far can we go with NV centers? I mean, NMR, we already know,
Yeah, I think so. If we look really at the NV center as a color center, the main bottleneck that is now there is the efficient extraction of photons. So, and there are two effects. So one effect is that you have a branching ratio that makes that if there's photon emission, actually only about 3% of the cases you get coherent photon emission, and 97% of the cases you get photon emission, but it's redshifted. So
Right.
you get photon emission and phonon emission, or actually the DMV molecule vibrates a little bit. If you want to read out the state, it doesn't matter because a photon is a photon. You're just counting photons. But if you want to make entanglement, you only want this 3%. And so that is, well, in these single photon schemes, you only hit by the 3% once, but it's still, a factor of 30 away from the most efficient you could do. So we're actually currently working on putting EMV centers in different types of cavities to enhance this.
Enhances, yeah.
Yeah, but I think more generally, I mean, there are other color centers, not only in diamond, but also in silicon carbide, etc., that have more favorable branching ratios. So often they have something else that is then maybe not as good as the EMV center, but I think the whole game will be in the next years to try to find an optimum where you have, sort of, it will not be the best of both worlds, but sort of the best available of both worlds. So
right.
And maybe also depending on what application you're targeting, you may want to sometimes you may want to use an EMV center, for example, for sensing and at room temperature. EMV centers are probably gonna be there for a while. But for maybe some other application, you want to use another type of center. And we are also looking in thin vacancy centers, for instance, in diamond.
Right.
Yeah.
Thanks. Yeah, thanks.
Yep.
Nunshik, you wanted to ask a question?
Yes, just a question. So for remote entanglement for any kind of repeaters scenario, do you also think of entanglement distillation or that kind of things? So if so, then do you have a strategy for that?
Yeah, good question. So actually, we have done one experiment, and we did a very simple form of entanglement distillation. So I can look at. I actually have that somewhere in the back of my slides. Yes. Wait. 1 minute. So this is an experiment we did in when was this? Published in 2017. Let me share my screen. So can you see this?
Yeah.
Yeah. So here an experiment. So maybe I should show this one. Maybe so this is just a very simple experiment, but it shows you maybe the way we're going. So in this case, we make entanglement between 2 electron spins. Then we swap the state onto the nuclear spin. We make another entangled state on the electron spins, and then we apply this distillation operation, and doing finally some feedback. And then out of this, see, I actually don't have the data. I do have the circuit diagram, but I don't have the data. But we could show that in this case, in a certain regime, the distilled state that came out was indeed better than the states that we put in. And then we also did analysis there in terms of E-bit rate. But I have to say this is still quite simple and quite limited. So in the end, you would like to have many of these nuclear spins, and then you make many of these entangled states, of course, and then you try to apply these distillation operations. But this is definitely in the plans. Yes, absolutely. Yeah.
So I have a question.
I have a question. Okay.
So essentially, one of the points which you have highlighted is that this the defects, along with your NV center, in the sense this carbon-13 and which carry the nuclear spins. Now, is there any way you can find a much purer system in your, or have you gone for much purer system? Because they could be a nuisance parameter too, in some sense.
Yeah. So since about, I would say 10, 15 years, the diamonds grown in the lab are actually better than, in terms of purity, better than diamonds that come out of the earth. So people are able to make isotopically purified diamonds. So you can enhance the number of carbon-13s or reduce them depending on the application that you want. And basically what you see is what you expect. So if you lower the concentration of carbon-13, you start with higher initial coherence times, right? Because you basically take away part of the decoherence channels. And also if you do these type of decoupling experiments and you want to reach 1 second, you just need less decoupling cycle. There are also experiments in which people put more carbon-13 because they just want to have more nuclear spins nearby. One interesting question is, what is the optimal concentration? Because you want to have, I mean, the nuclear spins for what we want to, they should not be too far away, because if they're too far away, the interactions will be very slow and doesn't really work. If the density is too high, then the, intrinsic, the decoherence of nuclear spin to nuclear spin becomes a very big factor. So there is some sort of optimum. And actually what's interesting is that we find that the optimum is very close to natural abundance. So, so actually what we have now is quite good for experiments. But of course, in the ideal world, what you would like to have is an NV center. And I say, if I want 5 nuclear spin qubits, I only have these 5 nuclear spin qubits and no other nuclear spin qubits. But that, if you think about what that means microscopically, this is very hard, because if you think about the distances, right, these carbon-13 nuclear spins, they are, like 5 to 10 lattice sites away. So you need to be able to control, have atomic control of how the diamond is built up on that scale. So you have to be able to put atoms one by one inside the diamond. This is with the usual growth techniques. They are grown using chemical vapor deposition. So you basically grow, layer by layer. You cannot control it. So you can control it in the plane, because you can grow sort of isotopically purified, stop, and then make a 2D layer of nuclear spins, and then stop, and then again. That you can do, but to have it 3-dimensionally controlled is at the moment very hard. Yeah.
And how is the spin coherence of the electron then depends? I mean, if you take away the diamonds, sorry, the carbon-13, then how then does it increase the coherence length by a huge amount, or that there's
it scales. Yeah, it scales. Well, okay, let me be precise. So what people have seen is that if you start to reduce it sort of orders of magnitude, you get the expected increase in coherence. But of course, at some point you hit another decoherence channel. And it turns out that in the diamonds where they do this isotopic purification, they have a little bit higher concentration of nitrogen in impurities. This usually has something to do with the purity of the gas. Its technicalities can probably be solved, but this is what people have seen. So at some point you start to see another spin bath, and this is then, and these are probably electronic spins of nitrogen impurities. And actually there are some nice experiments that have been recently done in Delft by Tim, and they're actually on the archive, I think last week or 2 weeks ago, so where they actually took one of these diamonds, so with isotopic purification, and then start to see, can we use these nitrogen electron spins as qubits? And they actually see that they can access these and also make an entangled state of 2 electron spins inside the diamond. So, I mean, in a sense, then you replace the nuclear spins by some other spins, but you can still play the same tricks.
And at these temperatures you're talking about, the phonon is not a big problem for you, the phonon bath? No.
So already at room temperature, the coherence time is in milliseconds. So there's very small coupling to phonons. Yeah. But at low temperature, I mean, there's basically nothing. That's, yeah.
Thanks.
Thank you. So I think there was a question by Dipankar Home earlier. He raised the hand, but now it's down again. So
okay. Hello, can you hear me?
Yeah.
Hello.
We can hear you,
Yeah. So Mike, it was an excellent talk for even for a theorist like me. I could follow much very clearly. Thanks very much. Now, a couple of questions. One related to the last slide you showed, that was about the tripartite case qubit study, that network. And then you mentioned about testing genuine tripartite entanglement. How did you actually, what was the procedure you did, or which type of inequality you tested?
Yeah. So I because this is all very fresh, I don't have proper slides for that. But basically, what we did in the experiment is that we made a GSC state distributed over the 3 nodes, and then we just analyzed that using standard tomography. So we just measured the state fidelity to the ideal GSZ state, making sure the fidelity is above 0.5, so that we know that the entanglement is genuinely multipartite.
Oh, in that sense, by doing.
Yeah,
And
yeah,
this
yeah.
is what you also did for your earlier GHZ study using 7 qubits. You mentioned earlier.
Yes, in those cases, so what we measured, right, so on the y-axis that had state fidelity. So we just measure in those cases, so that's data not from my group, but they just did state tomography and then measure the fidelity to the ideal state, and then checking at what point it dips below 0.5. And that is from 7 to 8 qubits.
Okay. So what was any particular motivation for testing GHZ state for for larger number of qubits? Any other type of study you are planning, or just a testing that a GHZ state has been produced?
Yeah, so I think it depends a little bit on who you ask. So so for example, in this network setting, we really see the GHZ state as a resource. Right, so the ability to be able to distribute GHZ state allows you to run different network protocols. Like,
but you do make use of its non-local feature. Means that's why you wanted to test its non-locality.
Yeah. Well, okay. We of course we have to be careful when we use non-local, because non-local has a sort of a formal meaning.
Yes.
Non-local in the sense that they are different nodes. Yeah. So in this case, they are not non-local in the sense that they are space-time separated.
So you did not test it by any other type of real inequalities, like Betlishny inequality or Marmin inequality.
Right. No. We didn't do that yet on these. No, and I think that's also a question to me. What can we still gain there?
Yes.
So my feeling is, of course, the GHZ inequalities are a bit different from Bell's inequalities, but in the end, you're testing the same things. My feeling is that the experiments of 2015 and 2016, right? There are 4 experiments that close the loopholes. My position is that we're done there. Like we've basically done everything we can. It's been shown on 4 different experimental systems. I think that doubt, if there was any doubt at all, I think that doubt is gone for me. So I personally don't have a lot of motivation to say, okay, now we also want to do that now with 3 particles against space-like separated, etc. But there are, I'm saying that there are, of course, variations on this. You may know there's this proposal by Nicolas Gisin and others to actually check whether if there's any spooky action, whether it's infinite speed or finite speed. So these things, but then you would actually need 4 nodes in a certain space-like configuration. So that is interesting, I think.
And that's where they're testing non-locality at the internet, quantum internet level. The GISA proposal. Yeah. So, and just another quick question: that contextuality testing you mentioned, that 8 dimensions. You mentioned your PRL paper, 2019.
Yeah.
So what was any particular motivation for that? So there also one can take the position contextuality had been already tested at more than 2 or 3 or 4 dimensions. So what was any particular motivation there?
Yeah, I think so. For that paper, there were 2 motivations. One was to do the GHZ test in a single shot, because that had not been done, and I really like that from a conceptual point of view.
Could you please repeat? I couldn't follow. You said determining in a single shot.
Yeah, the single shot meaning that you run that experiment and you get an outcome. And the outcome is +1 or -1.
So you are testing contextuality in a single shot.
Yes. So that was the motive. And the other one, where we go into 8 dimensions, there it's a bit more subtle, because there are also other experiments in this area. The game is always to make sure that you have compatible measurements, and how do you prove that? And that is a very tricky area. You cannot fully prove it, but there's a lot of stuff you can do to make sure that, you know, at least first the simplest errors are taken out, and then the more advanced errors, etc. And that is then done. I mean, I'm not a full expert in this field, but as I understand it, this is done by actually adding terms to your inequality. So it actually becomes harder to beat the inequality, but it also allows for your measurements to make certain errors. So instead of saying, okay, I assume my measurement doesn't make that error, I actually put that into the inequality.
Okay,
itself.
okay, I understand.
Yeah.
I know,
Yeah.
yes, what you mean. Okay, okay, excellent. Thank you very.
Can I ask you a question? Hi. I mean, as the subject of this series of seminars is also gravity, do you, I don't know, do you expect that your experiments can be used, for instance, to test any quantum aspect of gravity or something of this sort?
Yeah, it's an interesting question, and I think this will be a question to discuss after this talk. I would actually counter this question and ask you this, right? So, do you see any possibilities of taking these?
I mean, I am not an experimentalist, therefore I cannot. But
no, but maybe we need theory ideas.
Yeah, theory idea probably. They are works which many works has been done on the sort of model independent test of gravity, or for instance decoherence by gravity. But I mean, I know that it's very, very difficult to really experimentally present them, but as you are experimentalist, then you probably have a better idea how you can adapt your instruments to do such a test.
Yeah. That's I tried to bounce the question, but you're very good at bouncing it back again to me. No, I guess, I mean, if we in the general sense, what we need is to connect it somehow to something with mass, right? There's we're talking now all about spin states. They live in, you know, in the abstract Hilbert space, but somehow we need to connect this to mass, and then make sure that we, you know, that the dynamics expected from the laws of gravitation somehow, you know, come into play into the type of experiments that we are trying to do. I think that is the game to look at. So how can you couple this to with systems with at least some mass to think of good experiments?
Yeah, for instance, using, I don't know, heavy atoms in place of, for instance, or I don't know if it is possible, for instance, to see the difference between decoherence time of light atoms and heavy atoms or molecules. I don't know if such a thing can be adapted for your in your instruments and in the type of experiments that you are doing for the time being.
Yeah, it could be. I think we would have to look at that and explore. My expectation is that for sure the techniques that we are developing can be useful. It's not a priori clear that then the MV center is the best system to do it with. It could be that you want another center, but you are using the same techniques that we are developing. That could also be. But I think that is the exploration that can be done. Yeah.
Okay. Thank you.
If there's any other question, please raise your hand. Otherwise, we would formally close the discussion. But we would request Ronald to be with us for a few minutes so that we can have some informal discussions and all. So is there any question, last minute question? I don't see any hands. So if not, then please, let us thank Ronald for a wonderful, very exciting talk. So we are very happy to, you know, hear your talk today. Thanks, Ronald.
Thank you.